Hi, here is a quick video about springs because I had a comment by a YouTube viewer, Tlāloc, Mexicā. I did my best, and they said, what's the deal with springs? They don't get springs. And it got me thinking, I had students this semester in my in-person class say the same thing. We covered springs and they're saying, why are we talking about this? And I realized it is kind of strange in intro physics, we're talking about fundamental properties of the universe and masses just moving in an isolated system, and why do they keep moving and what makes them speed up, all these fundamental ideas, and then suddenly we say, now let's coil up a piece of wire and talk about what that does. It seems kind of specific and engineering-like thing to do when you're really just trying to talk about the fundamentals. I also realized there's this cool spring demo that I've never actually done before in a class or anywhere, so it'd be an excuse to show that. So I thought, why don't we talk about springs a little bit and give a little bit of big picture and why physicists are so obsessed with springs and talk about them in freshman physics.
I think you'll find it very interesting and a lot of fun.
And I'd also like to point out that based on other comments from Tlāloc, Mexicā, it's clear that they understand intro physics very well, and they do understand Hooke's law in a spring. So I'm not implying that they don't, but I thought it still might be interesting. So to think about a spring, it all really starts with the deformation of a material. So forget about the spring for a minute. Let's just think about a column of material or a thin wire, and it's got a cross-sectional area A, and it's got some length L. And let's imagine we apply a force to the end of it. Well, if we're getting away from our fundamental point particles for a minute and really thinking of this as a material, what will happen is you'll stretch it a little bit. So the end will move up, and you might stretch it some distance, delta L. And we describe this with something called the Young's modulus, or the elastic modulus. Basically the force per unit area that you apply, which is called the strain, equals some property of the material called the Young's modulus, y, times the fractional change in length. This is the stress. Fractional change in length is called the strain. And that's just the formula that's like phenomenological. We just find that if you apply a pressure, or you apply a stress, a force per unit area, you get a strain. And it's linear, right? If you apply a certain force, you get a certain delta L. Twice as much force, twice as much, constant, constant, constant. So it's linear up to small deformations. If you pull too hard, then things break and lots of bad things happen. So if you thought about springs a little bit, you might have seen the trick where you can kind of make this look like Hooke's law, that magic thing that springs do, where they always pull back towards their rest position in a way that's linear with how far you pull. So if we just rearrange this a bit, we can get force equals the Young's modulus times the cross-sectional area over the length times delta L. Okay, that's real small. Times delta L, like that. And you can see this kind of looks like that spring constant from Hooke's law. So you might say, no, wait a minute. I thought in Hooke's law there was a negative sign. Where's the negative sign? But you got to remember, here we're talking about the force we applied to this column that we're kind of thinking of as a spring. If it were a spring, we're applying Hooke's law, we'd be talking about the force the column applies to an object attached to it. So there's an action-reaction thing, and that's where you get your negative sign in Hooke's law, and you would probably call it X for an axis rather than delta L. So just an elastic column actually behaves just like a spring, and it obeys Hooke's law. All that's fine. So the problem is this makes a really horrible spring. In fact, I have a lecture called How Not to Make a Spring. I will link below if you want to watch it. And the reason is, a big part of it is this. This delta L, or this formula, is only true up to about 1%. It depends on the material. Some materials higher, some materials lower. Some materials don't do this at all. Go read about why rubber is allowed, or has what rubber does, and that'll be interesting. So what we have to do is find some way to engineer this to where maybe we can get a bigger extension than 1%. This would mean if you wanted a spring that lets you move something 1 centimeter, it would need to be a meter long to stay in this limit and to not break it. Another problem is this makes very stiff springs. So if we wanted to make some spring for freshman lab and we accepted it had to be a meter long to get 1 centimeter motion, it would also have to be incredibly thin, and probably you couldn't even see it for the kind of spring constants we would want. So lots of problems with making your springs like this. And that's why we make them like this. So you take that material, and if you coil it up in a structure like that, suddenly you get much bigger deformations for much shorter lengths without going to this limit where you're about to break the material. So let's think about why. It's clearly, if your first guess might be, well, we're just cramming all the length into this smaller volume. That's really not all it is, because if you just pull on this, you're not going to uniformly stretch this in this sense. There are softer deformations that are going to happen first. And one softer deformation is torsion. So similar idea here. There's lots of different elastic moduli. There's bulk and linear and shear and all these things. One of them is torsion. So if you just have this column and you twist it like this, you hold the bottom this way, you twist, it wants to spring back. So there's similar equations for torsion. You make a little angle, it wants to pull back by some property, depends on the area and the length and everything. But if you imagine that, now let's think, what if we added a little torsion to this? Well, that's what happens when you stretch it. You get a little bit of torsion, which makes, if we imagine this is the front of this coil and that's the back, and we give it a little torsion all the way through the material, then this comes down a little bit, which makes this front a little lower in the back, and it comes down a little bit. And every loop gets a little bit of a deviation down, and then it adds up. And when all that adds up, you can get a big change in the spring like that. So this is how you get a large deformation for a short spring, but still remain in this small limit where these equations stay linear. And torsion is one way to do that. So that's really that's the reason you have that shape, is you're not really stretching the material, you're twisting the material. And this geometry turns a twist into a large deformation that remains linear. Now, that's all fine. So maybe now you understand a little bit better about this geometry, but you can still ask why. Why do we cover this so carefully? And there the reason is because of this Hooke's law, because we have this case that the force and the deformation, or how much you displace it, is linear. So Hooke's law just tells you kind of static, or what the force is at any position. If you go try to understand what it does dynamically, if you start letting the mass and spring move up and down, we all know it's going to oscillate. So if you have this equation where it's linear, then the solution to that we can solve. We have an analytical solution. It's called a sinusoid, right? You can say sine is the answer, cosine is the answer. It's basically the same thing. But if it's some other equation, then it might be some nonlinear oscillation. Maybe you can't even solve it. It may not have an analytical solution. You might have to solve it on a computer. But this simplest case where the force and the displacement are linear that leads to the sinusoid, those are called harmonics. And we can use the simple motion of a sinusoidal solution and then add them up to describe complicated motions. And that gets into Fourier series. So basically the mass in a spring is really just a model for what we call harmonic motion. This idea that the force and the displacement are linear, and that leads to a very fundamental kind of motion that shows up all over the rest of physics. It doesn't really show up all over the rest of first-year intro physics. And that's probably why our obsession with masses on springs seems a little bit unusual, right? But that's the reason, is because it's a very fundamental initial kind of motion to talk about. So the reason I haven't shaken or started this spring yet is because it does something kind of special. And here I've kind of told you this simple story of how this works. This torsion happens and the thing just elongates. And another thing I want you to remember is nothing is ever that simple. There are many ways this wire can deform. There are many kinds of moduli. And what really happens in a spring are two motions. It goes up and down because of this torsion, and we're twisting the wire and causing each little loop to go down a little bit, and the sum is to let the whole thing go up and down. But most springs are designed so you don't see this, but as you pull it down, it also unwinds a little bit. Okay, so this spring is designed to make those about the same. So when it winds and unwinds, it looks like that. Okay, when it goes up and down, it looks like that. And usually a spring is designed where you don't see the wind and unwind. But if you have two mechanical systems that want to oscillate at a certain frequency, and they're coupled, that's clearly coupled, it's one structure, and their frequencies are close to each other, you get something called like a beat pattern. Like all the energy will be in one motion, and then it'll shift to the other motion, and then it'll shift back. So this is called a Wilberforce pendulum, where it's been designed such that those two frequencies are about the same. So you can see this up and down goes about that fast, And if I do that, you can see it's about the same period. So what we're going to do now is start it off just strictly in up and down motion and let it go and watch it for a minute. And you can see that starts to excite this twisting motion. And a lot of them will actually go completely into twisting motion. All the energy will go. This one doesn't quite do that, I think, because the wire is so stiff. If you make it with a thinner spring wire, it'll go completely twisting. But you can see we have quite a bit of twist now. It won't quite stop the up and down, but eventually it will convert completely back up to up and down motion. Okay, that's because there's really two kinds of Hooke's law happening with this spring. So let's think, what is the other one? So we did torsion in the wire to make the loops go up and down, but the other one is we have winding and unwinding. That's the motion you're seeing when the thing twists. So see, there it was just for a second, completely up and down. And now it's going back into the twisting. And in the winding and unwinding, there's not a modulus for that. It's actually kind of a complicated motion. You might think, well, maybe it's that the wire is expanding in the sense that we're talking here. Maybe we're just stretching the wire to unwind it. And again, that's too stiff. That's not really what's happening. As you wind it and unwind it, you're changing its radius of curvature of the wire. If we imagine it just simplified as it's a single loop, you're basically making the loops bigger. So what I'm going to draw is what it looks like when you bend a material and you change its radius of curvature, or what's easier to see is just take it from straight to bent. Let's think what kind of a motion, what that does, right? So here we have just the rigid material here that is unbent, kind of like this on its side, and now we give it some curvature, like that. And you ask, how did we make that happen? Well, you actually can look at it and you can say, well, there's some line here that's basically the same. And what we've done is we've stretched it on this side and we've compressed it on this side. Where those stretching and compressing basically follow this elongation modulus. We elongated this, and this formula also applies to compressing it, to pushing it down. And we've compressed on the other side. There's also other moduli. There's shear modulus that may come into play here. Every deformation is extremely complicated. We can make up these little simple combinations of motions, but they're all happening all at the same time. But I believe on the winding, unwinding, this is the dominant one, is that the material is already bent into a circle and we're just doing this kind of deformation to make the circle bigger and smaller. So there is more than you ever wanted to know about a spring and why we care about it so much.